So welcome back, everybody, to our little conference. We have two talks this morning, and our first talk is by Nataša, who needs no introduction. So please go ahead, Nataša.
Okay, thank you very much once again for the invitation. So I'm gonna discuss some recent results about the classification of ancient solutions in the mean curvature flow and the Ricci flow. And so here, like right in these talks, I want to address these two questions. And in the first talk, I'm gonna focus on the mean curvature flow. And then tomorrow, I'm gonna tell you more about the Ricci flow, okay? So that is the plan. So let me just briefly start with the mean curvature flow, right? So like just to set up the notation, for me, M sub t will be like a smooth ancient. It will be a compact solution unless I say otherwise to the mean curvature flow, satisfying this equation, right, where df dt is minus h times nu, where h is just the mean curvature of your hypersurface and nu is just the outward unit normal vector. And we all know that the mean curvature flow is a gradient flow of the area functional, right? So if this phi is just the embedding, you can compute the first variation of this area functional, and you can get that ddt of the area is just this minus the integral of mh times x dot nu, where x is just right this generator of the variation phi sub t, like I wrote on the slide. And we also know by the avoidance principle that every compact mean curvature flow has to run into a singularity in finite time, and we want to understand those singularities. That's usually the goal. And right, so one of the first results in that direction of understanding the singularities, at least in some special case, was the result of Huskin, where you start with uniformly convex compact hypersurface M0, right? And he then proved that the mean curvature flow starting at M0 has a solution up to some finite time capital T, at which the solution becomes extinct to a point in a round manner, which means that the normalized flow, right, exponentially converges to a round sphere as time approaches to plus infinity. And we also know that, right, so that at this first singular time, t less than infinity, we know that the norm of the second fundamental form has to blow up around the singularities, and we want to study those singularities by using the blow up procedure. So here I just wrote what I mean by that, right? So if like I want to rescale around pi ti, where ti converges to a singular time capital T, and let's say qi is just the norm of the second fundamental form at those points pi ti, which is this maximum, right, of the second fundamental form. Then I can parabolically rescale around these points pi ti, and I get this parabolically rescaled flow, which still satisfies the mean curvature flow equation, and I call it m tilde sub si. And when I take the limit as I approaches to infinity, you can easily see that this limit, if like is actually like a solution to the mean curvature flow, which exists from negative infinity up to some time a, where a can be anything from 0 to plus infinity, including the plus infinity. And these are like the singularity models, right, that you want to understand in order to understand the singularities. And you want to classify those solutions, right, that have the special property that they exist from time negative infinity. So, okay, so again, if capital T is the singular time, I'm going to just distinguish between two types of singularities, the type 1 and the type 2 singularity. Right, so type 1 singularity is when this lim sup as t approaches to capital T, where capital T is the singular time of t minus t, and then maximum of a squared is less than infinity. Then we say that we have a type 1 singularity, and otherwise we have a type 2 singularity. And similar definitions also hold for the Ricci flow. And these ancient solutions are the solutions, as I already said, that exist from negative infinity up to some finite time, capital T, and they model usually type 1 singularities, and eternal solutions usually arise as blow-up limits of type 2 singularities, and eternal solutions are the ones that exist forever from negative infinity to plus infinity. Okay. So examples of those solutions, the simplest examples are the solitons, which are the self-similar solutions, and they very often model the singularities. So I will just say that some examples, right, of solitons and also these ancient solutions that I have in mind are the shrinking spheres, the shrinking round cylinders, and the translating solutions. These shrinking spheres and shrinking round cylinders, they just move by homotheties. And these are the examples of ancient solutions. And the translating soliton exists forever. It's an example of an eternal solution and just moves by translation. Okay, so but the picture is not so simple because like also you have to understand all ancient solutions, which may not be only the solitons, because the solitons also satisfy, in addition to the mean curvature flow equation, also satisfy a nice elliptic equation that you can study. But right, as I said, like it's not always that nice because there exist also many ancient solutions which are not the solitons, right? Which just which don't satisfy like also a nice elliptic equation like the solitons. And the ones that will appear, as you will see in the lectures, in my lecture will be the compact solutions that you can visualize, right, by gluing two solitons, right? In this case, it will be two ball solitons. You can visualize them gluing by a cylinder in the middle. So you get something that looks like an oval. Okay. So it's very hard to classify ancient or eternal solutions in general, as you will see later, but you can try to do that under some natural geometric conditions. For example, what we did under some convexity conditions or non-collapsing condition. Okay. Okay, so let me just go like 50 years back and mention something, some old result, which, right, and then more recent result in early 2000s, which actually somehow motivated all this program about the classification of ancient solutions in both the mean curvature flow and the Ricci flow. So it's the kind of like, because what we want to do is kind of a real type of theorem, right, for those solutions. So if M is just a complete non-compact, right, Riemannian manifold, where Ricci curvature is non-negative, then there is a celebrated result of Yau, which says that if you consider any positive harmonic function U on such a manifold has to be constant, right? And so now the question is, does the analog of this Yau theorem also hold for the heat equation, right? Because that's somehow what we want to do for the mean curvature flow or the Ricci flow. But the answer, even for the heat equation, is that it's not true, right? So you don't get only these constant solutions. And you can take the example e to the x1 plus t, right, on Rn as a counterexample. But in 2006, Supla and Zhang, they actually proved the result that if you have a complete non-compact Riemannian manifold with Ricci non-negative, and if you assume that U is a positive ancient solution, but which has a certain growth at infinity, right? So if you assume that U has to be e to the little o of distance to some fixed point p plus the square root of t, as distance approaches to plus infinity, then they concluded that U has to be constant, right? And then you have some type of Liouville type of theorem. And if you drop the positivity condition, right? So if you just assume that you have an ancient solution to the heat equation, then you need to assume a bit stricter growth condition. You have to assume this like little o of distance plus square root of t, right? So in the first case, you can allow some exponential growth, but in the second case, if you drop positivity, you can allow, right, this linear growth more or less. And the proof in both cases uses this local gradient estimates of Liao type for this heat equation. Okay, so the next I want to just mention the semilinear heat equation, which is like one step right above when you introduced also this nonlinear term u to the p. And the result that I will mention hold in this range for p when p is in between 1 and n plus 2 over n minus 1, n minus 2, where n is the dimension. And it turns out that this semilinear heat equation actually is a good prototype for the blow-up analysis in geometric flows, in particular the Ricci flow and the mean curvature flow, when you want to study the neck pinches, right? So when you take the mean curvature flow or the Ricci flow and linearize them around the cylinder, you get like the same linearized operator. And then you can carry over some techniques from the semilinear heat equation to the Ricci flow or the mean curvature flow when you study the neck pinches. And so if U, right, is a solution to the semilinear heat equation, it's known that it exists until like the smooth solution exists until the L infinity norm of U blows up to infinity. And what I wrote here, right in the first line, is just the type 1 rescaling for the semilinear heat equation. And then after you do this scaling, Giga and Kohn proved that the L infinity norm is always bounded uniformly. So you always have somehow type 1 blow up in this case. And you can compute the evolution equation for W, right, which is also, right, W sub tau is Laplacian W minus 1/2 y dot gradient W minus W over P minus 1 and plus W to the P. Okay, and now if you want to understand the singularities of U, right, you need to analyze the blow-up behavior of U at the singular time. And for that, you need to understand those solutions to equation star. And in order to understand these solutions and even to classify these ancient solutions to this equation star, you need to understand the long time behavior of W as tau approaches to plus infinity and negative infinity first. At least that's what appeared in papers of Merle and Zag. And right, so what they studied in their papers, right, in order to understand the singularities of semilinear heat equation, is to give the classification of bounded positive eternal solutions W to this equation, which we also had on the previous slide. And these solutions exist from negative infinity to plus infinity. So what is easy to find is that the steady states of this equation star are either 0 or k, where k is just given by this very precise constant in terms of p. And Giga and Kohn proved that the limit of this W as tau approaches to plus or minus infinity are just the steady states. So it's either 0 or k. Okay, but besides from those steady state solutions, that there also exists some other which are space independent but still time dependent eternal solutions to equation star, which are given by this phi of tau, right? It's equal to a constant k times 1 plus e to the tau raised to this power negative 1 over p minus 1, right? So what Giga, Kohn, and Merle and Zag prove is the following result, that if W is like a positive eternal solution to that equation star, which already occurred on two slides earlier, then they classified all of them. They said that they have to be either the steady states, namely 0, or the constant k, or they have to be those space-independent solutions W. Right? So they completed the classification, and we were inspired by actually their techniques to classify those eternal solutions to the rescaled semilinear equation. What is one of the main steps in their paper is the following. So as I already said, right, like what also turned out to be important in our case, that you need to understand first the behavior of this rescaled solutions, or these eternal solutions at time negative infinity and plus infinity. And they showed that these limits can only be the steady states, right? So, and we already know the classification of steady states, it's either K or 0. And what is also easy to see that if the limit at negative infinity and plus infinity is equal to K, then your solution has to be equal to K for all times tau. And if the limits forward in time and backward in time at infinity has to be 0, then the solution has to be identically equal to 0 for all tau. But the most difficult case is the one that connects like the limit K at negative infinity and the limit 0 at plus infinity. Okay, so in that case, they wanted to prove that their solution W has to be exactly of this form, that right, W is equal to phi of tau minus tau naught, right? So these are like these independent of space solutions. So what they do, they take their eternal solution and they linearize around the limit, the backward limit, which is kappa, right? And then they compute the equation for V, where V is just the difference. And it turns out that, so here there is a typo. So it should be V sub tau is equal to L of V plus F of V, where F of V is just the error term. And it, right, so instead of this V should be L of V. So there is a typo. And L is just this nice linear operator. And you can recognize that this is exactly the same linearized operator that appears in the mean curvature flow or the Ricci flow when you linearize the operator around the cylinder. Okay, and so this operator is self-adjoint with respect to this weighted measure e to the negative y squared over 4 dy, and the spectrum is completely well understood, and it will also appear in our work. So there are two positive eigenvalues, 1 and 1/2. Eigenvalue 1 correspond to the eigenvector phi is equal to 1, and there is a 0 eigenvalue, and then there are countably many negative eigenvalues. And the eigenvectors are also very well understood. These are just Hermite polynomials. And then you can decompose the Hilbert space in these H plus, H0, and H minus spaces with respect to these projections onto the positive, neutral, and negative eigenspace. And then you can consider this, what I called, what I wrote gamma plus or minus of tau and gamma 0 of tau, which are just the norms of the projections of V. And remember what was V? V was just the difference between the solution and the backward limit, which is just the steady state, kappa. So you can then compute the system of ODEs that these gamma plus, minus, and gamma 0 satisfy. And they proved this very nice ODE lemma based on that system, right? They could actually prove that either like the dominant mode is either the projection on the 0 eigenspace or the positive eigenspace, right? So everything is dominated either by the 0 projections or by the positive projections. And then in their work, they deduce, like with lots of work, that the dominant mode is the one corresponding to the positive eigenvalue. And then there is more work involved than to show that this forces, so this conclusion then forces the solution V to be just phi of tau. And that finishes the proof. Phi of tau was just this space-independent eternal solution to equation star, right? So once again, so I will just emphasize that what was very important here is the spectral analysis and this ODE lemma, right? So, and this ODE lemma is very short, but it turned out to be very powerful even in our work, because we could also apply it, right? So let me just now turn back to our case where we consider like, right, non-collapsed solutions to the mean curvature flow. And this was introduced by Wei-Ming Sheng and Xuejie Wang. This condition was introduced by them. It just means that right? So you will say that your hypersurface is alpha non-collapsed if at every point P you can find these balls, B interior and P exterior, which are of radius at least alpha over h of P, which are tangent to the hypersurface and to each other at the point P. And what is even more remarkable is the result of Ben Andrews, who proved that this condition is preserved by the mean curvature flow. And of course, it makes sense only for mean convex mean curvature flows. And in that case, then we know that the singularity models are also non-collapsed. But we also know that if you take the convex and compact and self-similar mean curvature flow solution, then we know it has to be a sphere, right? So then we don't want to consider those self-similar solutions in our classification, because we know that if they are self-similar, they have to be the spheres. So I will introduce the definition of ancient ovals, and that will be for me any compact and alpha non-collapsed ancient solution to the mean curvature flow which is not self-similar.
Sorry to interrupt. Just had a question in the chat. Just going back a little bit to the Merlin Zarg result, as to why the lambda 2 eigenvalue dominates rather than lambda 1.
Oh no, lambda 2 dominates. I'm sorry. That's a typo. Lambda 2 is equal to 1. Yeah.
Right. But just wondering why that is, why lambda 1 doesn't appear as well.
Well, I mean, there is a work involved in that. I mean, it's not that easy to see. So,
okay.
Right. So, I mean, these I just wrote the outlines, but there is a lot of computations and also, I mean, it's not even right. So it's not even like clear right away why lambda 1 dominates versus to lambda 0. So,
okay.
Yeah. So you have to use the properties of your flows, that some eigenvalues just correspond to rescaling or change in time. So then, you can just perturb them away somehow. Yeah.
Thanks.
Like that's what happened. I mean, that's what happened in our case when we had to decide between lambda 0 and lambda 1. We had to rule out the case for lambda 1, and it was coming just from changing like the time of the extinction somehow. So it was, so we could somehow like perturb this away in some sense. But there, I mean, like this all involves the arguments. It's not like straight, it's not like easy to see right away. So that's what.
Thank you.
Yeah. Right. So here I will also then mention a result of Sujia Wang and also Theodora Matt and Hinalia, who considered the collapsed solutions, convex ancient solutions to the mean curvature flow in one of their recent works, and they proved the existence of those. And they also proved that they are unique in the class of rotationally symmetric convex ancient solutions, and they are known as ancient pancakes. So now what we want to do is to give a classification of all ancient ovals, right? So how do we know that that some example of those exist? So by Brian White, actually proved the existence of those ancient ovals with OK cross OL symmetry, and Robert and Orr more recently, they gave detailed construction of those solutions, also provided the proof of the existence, and also described those solutions more precisely, gave more asymptotics of those solutions. And then in the earlier work with Sigurd and Toti, we considered those ancient ovals. First of all, we considered at the beginning only those solutions which are ancient ovals, which are rotationally symmetric. And then we proved that they all have to have unique asymptotics as t approaches to negative infinity. That was the first step towards the classification of those solutions. And let me just on this slide briefly tell you what is the example of those ancient ovals that you can keep in mind that were constructed by Brian White and then by Robert and Orr independently. So you fix an L and then you construct a compact solution M sub L in the following form. So you take this generalized cylinder or part of a, just piece of a generalized cylinder, part of a generalized cylinder, Sj cross minus LL to n minus j. And you then put smooth caps at the end of these truncated generalized cylinders in a smooth way, so that you get like a strictly convex and smooth surface. And you use that as the initial data. These are all n minus j plus n uniformly convex, in the sense that the sum of the first n minus j plus 1 principal curvatures is greater or equal than some beta h for some fixed beta greater than 0, independent of L. And then you start evolving them by the mean curvature flow. Then you would like somehow to take the limit as L approaches to infinity and to produce some ancient solution which is different from a sphere. So you have to be a bit careful how you do that. So first you use the spheres as the interior barriers and cylinders as the exterior barriers to show that the extinction times of those solutions M sub L are all independent of L and are uniformly close to 1 in some sense, comparable to 1. And then you take those solutions and you rescale them, you shift their extinction time, you bring the extinction time of all of those solutions to 0. And then you also rescale them in such a way around so that the ratio between the major and the minor radius at a certain point is equal to 2. And you rescale around those points in space and time. And then you take the limit of those solutions, of those rescaled solutions at L approaches to infinity, not of MLT, but of the rescaled solutions. And then you have to do a little bit more of work to show that these are like these ancient solutions to the mean curvature flow, and they are different from the spheres because of the way we rescaled at the beginning. Okay, so they do exist and they are not solitons, right? So I will just tell you like on the next slide, like what is our theorem, but now I will just say that roughly our theorem, which tells you that all ancient ovals have the same asymptotics, meaning they have the same asymptotics as the asymptotics of this ancient oval constructed by Brown White and Robert and Orr, right? And you will see that they look more and more like a cylinder as time approaches to negative infinity, and around the tips they look like ball solitons. That's why I said you can view them as two ball solitons glued together with a cylinder in between. And to prove this theorem, we use what we do, like we somehow, as I said, were very inspired by the proof of Merle and Zag, because we know that our backward limit as t approaches to negative infinity of the rescaled flow is around cylinder in our case, because we are concentrating to the case where the backward limit is just around cylinder, not like a generalized cylinder, but just around cylinder as n minus 1 cross r. So we linearize around that, and we studied this linearized operator, which is the same as in the case of the semilinear heat equation. So we know the spectrum very well. But then we need an additional step. We also need to construct some barriers, right, which will help us do our estimates and obtain the right asymptotics. So that was a pretty subtle also point in the proof. And so here, like you see our solution M sub t, we are assuming at the moment it's rotationally symmetric. So if U is this, is big U is the profile function, then it satisfies this very simple equation. U sub t is UXX over 1 plus UX squared minus n minus 1 over U, okay? And then we do some parabolic rescaling that I will mention later. And then we take our rescaled solution and consider the difference of the rescaled solution and the cylinder, because the backward limit is the cylinder. So we do something very similar to what Merle and Zag did. And then we just project, right, the difference from our solution of our solution from the cylinder to 0 positive negative eigenvectors, eigenspaces. And then we compute the system of ODEs, which is satisfied by the norm of those projections. And then we have to argue that we are in the situation to apply the ODE lemma. To argue that we are in the situation to apply the ODE lemma, because we have to also introduce the cutoff function. That's why we need the barriers also. Okay. But then if when we do that, right, when we justify that we can actually apply this OD lemma of Merle and Zag, then we can obtain this description of the asymptotics in the rotationally symmetric case, right, at the moment. So we have the parabolic region. So I will just say that the u of y comma tau is just parabolically rescaled solution, right? Big U is unrescaled solution and little u is just parabolically rescaled solution. And in this parabolic region where your solution looks like a cylinder, okay, so you get that u is square root of 2n minus 1 times 1 minus y squared minus 2 over 4 tau and plus little o of tau to negative 1 when y is less or equal than L, right? So in compact sets in y, what you can see is like you see the square root of 2n minus 1, that is just a cylinder. And then this, okay, this is like the this is the first order asymptotics, and then this y squared minus 2 over 4 tau is the second order asymptotics, right? That will come from the application of this OD lemma of Merle and Zag. Okay, and that is exactly the y squared minus 2 is exactly like the eigenvector that corresponds to the 0 eigenvalue. So in our case, actually the 0 eigenvalue will prevail, right? Unlike in the Merle-Zag case where it's like the positive one. And because we are in the compact case, right? Also, and then by using the barriers, you can also obtain this precise asymptotics in the intermediate region, which is the region that connects the cylinder and the tip, right? So you get these kind of ellipse, parts of ellipsoids. And then in the tip region, you can show that at the two tips, when you rescale, right, by the right scale, which is like the H max, then your solution converges to the ball soliton of velocity 1. And from all these asymptotics, you can even get very precise asymptotics for the diameter and for the maximum of the mean curvature in this case. Okay, so this is like, as I said, like this is where work of Merle-Zag was a big inspiration for us to obtain those asymptotics. And so after our work was done, then Brendle and Choi did the non-compact case, right? But before I mention the result, I will just say, because I was mentioning this ball solution, that it's just the unique convex rotationally symmetric translating solution to the mean curvature flow that satisfies this nice elliptic equation, right? It's graphical, and the graph U satisfies this nice elliptic equation. And then, right, Brendle and Choi, they were considering non-compact, strictly convex, and uniformly two convex. So what it means that like the sum of the first two eigen principal curvatures are like greater or equal than some beta h for some fixed beta, right, which is independent of time, and non-collapsed ancient solutions to the mean curvature flow, and they showed it has to be the ball soliton. Right, so in their proof, there are two steps. The first step is that they prove that this solution has to be rotationally symmetric, and then once they know it is rotationally symmetric, right, they prove that it is a translator, and once it is a translator, then has to be the ball soliton, right? So, and as a corollary of that result, you get that if you start with any closed two convex hypersurfaces, after evolving it by the mean curvature flow and running into a singularity, the only possible blow-up limits are the spheres, the cylinders, and the ball soliton. So now, like, we looked at their proof of rotational symmetry, and then we thought, okay, maybe we can try to modify it somehow and to use it in our compact case to prove that in our case, every ancient oval has to be rotationally symmetric, right? And then try to prove the uniqueness by using our precise asymptotics of rotationally symmetric ancient ovals. So that was like our idea after we saw this paper of Brendle and Choi. And then together with Angenent and Daskalopoulos, we proved that if you have a uniformly two convex ancient oval, right, then up to ambient isometries, translations, and parabolic rescaling, this M sub t has to be either a family of shrinking spheres or has to be the White's ancient oval. Or I will just say the ancient oval. And so like similarly to the proof of Brandle-Choi, our theorem has two steps. First, we use the arguments of Brandle and Choi, and we adapt them from non-compact to compact to the compact case, right, to prove rotational symmetry, right? And also, like in the proof of the uniqueness, what plays an important role is, of course, the global convergence theorem of Robert and Kleiner and the cylindrical estimate. So the global convergence theorem just tells us that if you normalize the mean curvature flow by the mean curvature at a single point, then you can pass to a subsequence, right, which converges globally and smoothly on backward spacetimes. And the cylindrical estimate tells you that if you have alpha non-collapsed flow, which is uniformly 2 convex, then for every epsilon greater than 0, there exists some delta, so that if you know that the quotient between lambda 1, which is the smallest eigenvalue, and the mean curvature is less than delta, then you are somehow in the cylindrical region, right? You are epsilon close to a round cylinder. So I would say like these three things played an important role in proving that our solution is rotationally symmetric always. And I will just mention maybe key ideas in the proof. So I will remind you that our setup is that we are considering uniformly 2 convex ancient ovals. And the first thing that we do, we have to prove some structural type of results for our solutions, right? So we take any sequence xj in mtj, and any sequence of tj is going to negative infinity, right? And then for every xj tj, where tj goes to negative infinity, we rescale the mean curvature flow by the scaling factor, which is just the mean curvature at xj tj, right? We rescale around xj tj, and then you can show that the limit is always either the ball soliton or the shrinking round cylinder. And both of these things is rotationally symmetric, ball soliton and also the shrinking round cylinder. So that is the first step. Right. So now, like, right. So this means that your solution. So the next step, the next step after we know that is to show that your solution really roughly looks like a cylinder, which has 2 balls attached at the ends, right? And the other very important ingredient that we use in the proof is the neck improvement theorem, which was actually proved by Brandle and Choi. Let me just tell you briefly what that is. And so if I'm now going to go to dimension 2, but you can generalize this to any dimension n, right? So, but just for simplicity, I will just consider surfaces in R3. And if K is any vector field in R3, you will say that it's normalized rotation vector field if there exists an orthogonal matrix S, so that K is similar to this matrix J, rotational matrix J. And then you will say that your point X bar T bar is epsilon symmetric if there exists this normalized rotation vector field in R3, so that K nu times H is less than epsilon in this parabolic neighborhood, which is of the size of the mean curvature at the point X bar T bar, right? On a scale of this parabolic neighborhood, what I mean is on a scale of the mean curvature at X bar T bar, right? So Brandle and Choi in their work established very important so-called the neck improvement theorem, which actually tells you that if you are in the cylindrical region, namely if you are in a neck, it becomes even more symmetric, all right, under the evolution of the mean curvature flow. And this neck improvement theorem can be applied not only if you have just the ancient solution. You don't have to have an ancient solution, but you can have like a solution which is defined on a sufficiently large parabolic neighborhood. And since here we have an ancient solution, we will make a use of it to say that we also can iterate this and be even more and more symmetric until we prove that you have to be actually rotationally symmetric. So here is the more precise statement of the neck improvement theorem. And what I will just say, the importance of it is that it's not applied only for the ancient solutions, but also for the solutions which are defined in large parabolic neighborhoods around around the considered points. So it says that for every epsilon greater than 0, you can find some L big and epsilon 1 small, so that if you consider this parabolic neighborhood, right, which is on the scale again of the mean curvature at x bar t bar, right, and if you assume that every point in that parabolic neighborhood lies at the center of epsilon 1 neck, right, and if this point x bar t bar is epsilon symmetric, then you can they show that x bar t bar is epsilon over 2 symmetric, right? So they improve the symmetry, having that the solution lies in a large parabolic neighborhood in a neck region. So now, since we have a compact solution where we look like a cylinder and we have these two balls attached at the ends, we also have to prove the so-called cap improvement theorem, namely that the symmetry also improves in the cap regions, right? And so we have the analogous theorem, which is stated very similarly to the neck improvement theorem. For every epsilon, you can find L1, T1, and epsilon 1, so that if you consider this parabolic neighborhood centered at x bar t bar, again, everything is on the scale of the mean curvature at x bar t bar. And if that entire parabolic neighborhood is epsilon 1 close to a ball soliton, and the center of that neighborhood x bar t bar is epsilon symmetric, then you show that x bar t bar is actually epsilon over 2 symmetric. Okay. And now, okay, there is an argument here, right? But the argument involves basically the iteration and the fact that you have an ancient solutions, so that you can actually go all the way up to time negative infinity. So if you do these iterations and iteratively apply the neck improvement and the cap improvement theorem, you can prove that your solution is rotationally symmetric. So now we know that every ancient oval is actually rotationally symmetric. And now we managed to do two things. We know every ancient oval is rotationally symmetric, and we know that all rotationally symmetric ancient ovals have unique asymptotics. Now we want to use that to prove the uniqueness. And then there comes this theorem, which I already had on the previous slide, but I'm just going to remind you that if actually, no, I didn't have exactly this theorem, but now since we know that the solution is rotationally symmetric, I can put that in my hypothesis. So I consider the ancient oval, which is rotationally symmetric, then it is unique, right, up to scaling translations in time. And you just get you only get this White's ancient oval, basically. So the proof of this uniqueness so for that, we need to introduce the cutoff functions, and basically we consider two regions, the cylindrical region and the tip region. So, right, this, whatever we call the intermediate region, this is more or less part of the cylindrical region, because if you rescale by the mean curvature around those points in the intermediate region, you will still see the cylinder, right? So you basically have two regions, the cylindrical and the tip region. And what we do, we prove coercive type of estimates in two regions with respect to the appropriately chosen weighted L2 norms in both regions, and then you put these two estimates together, and you conclude the uniqueness. And again, like even in the proof of the uniqueness, you will consider this linearized operator around the cylinder, and you will use the spectral properties of this operator, like what we did also in the proof of the precise asymptotics. Okay, right. So, so I already told you that we have these two regions and that we prove coercive type of estimates in these both regions. And these coercive estimates are based on, like, we cannot prove them without knowing that our solutions are almost the same, right? Because we will actually consider the difference of two solutions, right? So the proof of the uniqueness will go by contradiction. We will assume that we have two solutions, U1 and U2, and then we will consider the difference, U1 minus U2. So this is what I mean here by the distance function between the two given ancient solutions. And we will consider this difference in these appropriated weighted L2 norms in each of the regions. And then, right, so now we know that this U1 and U2 have the same asymptotics. So then the proof of uniqueness will be based on that. And then based on some Poincare type of estimates, which we need to prove for these appropriate weights. Okay, so but then there is an extra difficulty here, because if I give you any solution to the mean curvature law, let's call it M of t, right? This gives rise to a two-parameter family of solutions, right? M gamma beta, because we call it M gamma beta, and it's what I wrote here, e to the gamma over 2, M e to the minus gamma times t plus beta. So what you see, beta corresponds to translations in time, and gamma is just like corresponds to the scaling or dilations of your solution, parabolic dilations of your solution. Right? So if I give you one solution, I can produce infinitely many, right? By choosing different parameters, gamma and beta. So we have to rephrase our theorem in the following way, that for every two ancient ovals, we can find parameters gamma and beta, so that M1 is equal to M2, but after we, after we do appropriate parabolic rescaling and translation in time in my solution M2, so that I produce M2 gamma beta. So M1 is equal to M2 gamma beta for certain values of gamma and beta. Okay, so so what we do, we parabolically rescale by the square root of t minus t, right? And then big U, remember, was a profile function of unrescaled solution. And this little u, I call the profile function of the rescaled solution, right? And here I wrote like what u beta gamma is in the rescaled variables. U beta gamma is a profile function that corresponds to this m gamma beta here, okay? And now what you do, you look at this difference, right? W is U1 minus U2 beta gamma. I'm not really taking U1 minus U2, but because I have to incorporate also these parameters, beta and gamma, that I already told you about. So, right, so I'm taking this difference.
Nataša,
Yes.
do you mind if I ask a quick question? Do you have to worry about translations along the axis of rotation here at all? Spatial translations along the axis of rotation.
No, so we only worry about translations in time and dilations here, because somehow we fixed the center there. So
yeah, okay, thanks.
Right, so I mean, so we have only these two parameters, right? I mean, like, and for my before I know, before we even prove rotational symmetry, right? You will assume that up to ambient isometries, the axis of rotation will be the same for two solutions, right? So that's why in the statement of the first theorem, we say up to ambient isometries and dilations and translations in time, and we fix the center once we know the solution is rotationally symmetrical. Okay. Okay, so as I said, we have two regions, the cylindrical and the tip region. And then we introduce these cutoff functions, phi sub c and phi sub tau, where phi sub c has a support in the cylindrical region and phi sub tau has a support in the tip region. Right? And then WC and W tau are just like the difference W multiplied by the corresponding cutoff function. Right? So now, like, so I already told you, WC is just W, where W is the difference between these two solutions times the cutoff function supported in the cylindrical region. And you can then compute the equation for WC, and you can write this in write it in this form. L is just the linearized operator of your of the mean curvature flow around the cylinder, and then plus you have this error term, but the error term depends on W and also the cutoff function, right? So, and that's always the biggest problem, that these error terms depend on the cutoff functions. Your linearized operator is nice. We already saw it, and it is self-adjoint, right? With respect to this weight, e to the negative y squared over 4. And as before, I'm going to call P0, P minus, and P0, P plus, P minus, and P0 to be the orthogonal projections onto these positive, negative, and zero eigenspaces of this operator L. And now, like, what was very easy to figure out is what should be the weight in the cylindrical space. So it is exactly this weight here that comes from this operator being self-adjoint when you linearize it around the cylinder. So this is the right weight to take in the cylindrical region. And here we define the norm, right, in the cylindrical region that we will work with. Okay, so this was very straightforward and is easy to figure out. What was much more difficult was to figure out the weight in the tip region. Okay, and so now I'm going to call W hat sub C, right, to be just the projection of this difference on the positive eigenspace and the projections of the difference on the negative eigenspace, right? And somehow I want to say that the norm, at least in the cylindrical region of this part, is controlled by the positive projection, right? So that is somehow my goal again. But again, remember, you are working with cutoff functions. So in the first step, you cannot quite get that. So what you can get is this estimate, which I called star P, and which tells you that this W hat sub C is controlled by some epsilon, where you can take this epsilon as small as you want if you go backwards in time sufficiently. If you go sufficiently backward in time, namely by choosing tau not sufficiently small, right? You can make this epsilon as small as you want, and you can see that the norm of W hat C is controlled by the full norm of WC, and then plus we have this term here, W times chi, right? Where chi is the cutoff function which is supported in the transition region between the cylindrical and the tip region, right? And that comes because of the cutoff functions that we have, right? If we did not have this term, right? If we did not have the second term, then the estimate star P would tell us the W hat sub C is basically little o of the norm of the projection of this difference, right, on the zero eigenspace. And then we would be in a very good shape, because then we could take our equation, just project it on the zero eigenspace, carefully estimate the error terms, and then try to hope that the zeroth projection is identically equal to 0. Okay, so I mean, that's what we would like to obtain. But unfortunately, because of the cutoff functions, we also have this second term that we somehow have to deal with. And I will also say that how these parameters beta and gamma come into the game to obtain this estimate star P. Okay, you have to choose parameters beta and gamma so that at some sufficiently small time tau naught, these projections P plus and P0 of the difference W sub C is equal to 0, right? Because otherwise you cannot obtain an estimate like that. So that's how you make your choice. So as I said, right, so this star C is the same as this star P, right? So I just called them differently, but this is the same estimate, this star C. So you have to control this term here, W times chi, where again, chi is the cutoff function which is supported in the transition region between the cylindrical and the tip region. And what you do next is, right, you want to prove the estimate star star, where this W hat is controlled by WC, by the norm of WC. And then what we managed to prove is this estimate star star, where this coefficient is even given by C over tau naught. So this can be made as small as you want by choosing tau naught, right? Very negative. And you see, like, once you have the estimates star C and star star, you can combine them and you can get the estimate that we were hoping for, that the norm of the difference, the norm of the projection of the difference on the positive eigenspace and the negative eigenspace is controlled by the projection of a difference on the zeroth eigenspace. Right, so this once you have this estimate, you are in a very good shape, because as you will see, we will now project the equation on the zero eigenspace, and then we will prove that this P0 of WC has to be identically equal to 0, which will give us then that W hat C has to be 0, and also W in the tip region will have to be equal to 0. So our difference W will have to be equal to 0. But since I'm gonna run out of time, maybe I'm gonna tell you a little bit more. Maybe I'll just continue tomorrow, and then I'll just finish this, and then I'm gonna tell you about the Ricci flow. Okay, but before I finish, right, I will just say that right, our goal is to obtain this WC, right, that we have here. And for that, we need to prove the estimate star star, which is basically the estimate coming from the tip region. And there you have to choose, right, the appropriate weight in the tip region. But I'm just going to say that in the tip region, you have to switch the variables y and u, because u is equal to 0 at the tip. And then you have to consider this other equation for big Y as a function of u, right, which is written here. And now you will have two solutions, y1 and y2 in the tip region, and then you will consider this difference big W, right, in this different parametrization. And then the weight that we will define in the tip region will be given in this parametrization, but then you have to make sure that the weights in the transition regions are also equivalent, because you want to put these two estimates together. Okay, but maybe I'll just tell you that next time, right? So how we obtain just this estimate in the tip region and how we put them together just to prove the uniqueness. So I'll just finish.
Thanks very much, Nataša. I do have one sort of naive question. So in terms of proving the rotational symmetry, the kind of, I guess, an obvious thing to try and do would be to apply a parabolic Alexandrov reflection method.
Right.
I'm just wondering why that doesn't really work here.
Oh yes, we were like thinking about that. That was our first thing to try to do, but then we just couldn't adapt it to this ancient parabolic equation somehow. We just couldn't do it, but we tried that a lot. Yeah. That was the first natural thing to try to do. I agree. Yeah, but we couldn't do it. So then we said, okay, let's assume rotational symmetry. Then we got the uniqueness and the rotational symmetry. But then when we saw the paper of Brendel and Choi, we said, okay, but you know, like, okay, they're in the complete setting, but I mean, our case is like somewhat similar because we just have the ball on the other end, right, to close it up. So then we looked and tried to modify their arguments, but it would be nice to see if, right, some simpler argument could work, right?
Yeah, I guess you would need quite good control on the asymptotics. Is it? I imagine somehow you lose control of the scale of the bowls or something, and that would, if you don't have a very.
Yeah, I remember the problem was that we looked in that direction what was done, and all papers what we could find was like were like elliptic ones, right? And then for the parabolic ones, like, since we have also these ancient things, you are saying we were losing control over something when we went to negative infinity, so we just couldn't make it work.
Yeah. Okay, interesting. Thank you.
So I have a question. Have you thought about these other ones with different kind of symmetries so that they're not rotationally symmetric, or this is already like too complicated? Like, would you be able to adapt all these things to something that has different kind of symmetry? So Angenent has this proposed asymptotics.
You mean for OK cross OL symmetry?
Yeah.
Right, but there is a paper of Robert and his student who proved the uniqueness assuming OK cross OL symmetry.
So is this like for translators or ancient solutions? Like
For
I saw
ancient
the
solutions, for closed ancient solutions, yeah.
Oh, okay.
Right, so they adapted these methods like to prove the uniqueness in that setting, yeah.
And presumably you don't get uniqueness once you drop there are additional examples if you drop the
right, but they also construct, yes, they in the same paper they construct examples which are not right. Yeah. So you cannot expect to have the same result if you drop right the assumption on the symmetry. I agree.
Okay, but and then there are known the precise asymptotics, how like you have to scale to get the translators and stuff.
Yes, like they also do. I mean, they wrote 2 papers, right? So in one of the papers, they prove the uniqueness in this assuming the symmetry, and they construct those solutions, right, which are not ancient ovals, right, but are the solutions with OK symmetry only, let's say. And then there is the second paper where they give the asymptotics, and up to the first order, they have the same asymptotics, yeah. So the difference between those solutions comes like somewhere in the second order or something.
Oh, nice.
Okay, great. Thank you again, Nataša, for a great talk. Really good to see all of those arguments.